So in addition to that group, there's also, of course, a number of unsaturated fatty acids, unsaturated long chain carboxylic acids that are also, relatively important to us. And these include things like palmitoleic, oleic, linoleic, linolenic, and arachidonic. And, we find these in a number of sources. Palmitoleic makes up about 20% of what we find in macadamia oil. Oleic we find in pretty much any cooking oil. We use olive, corn, peanut oil. Linoleic and linolenic are both found in a lot of nuts and seeds. And arachidonic acid, we actually find that it's fairly abundant within the brain. These range from 16 carbons up to 20 for arachidonic. And each of these have one or more cis alkenes in them. So palmitoleic has one cis alkene. Oleic also has one cis alkene. There's two cis in here, 3, and 4. And most likely, if you take a biochemistry course in the future, you'll learn more about some of these types of acids. The other group of carboxylic acids that we see have a lot of common names are when we deal with diacids. So diacid being a molecule that has a carboxylic acid group at both ends. And the first 6 of those, from when there's 0 carbons in the middle up to 5 carbons in the middle, are fairly important, fairly common, and have, widely used common names. And those are oxalic, malonic, succinic. And things like malonic acid and succinic acid, we see a lot of them as well as their derivatives in biological processes. Glutaric, adipic, and pimelic. And in a moment, I'll give you a bit of a strategy to help remember these names. But first, I want to show you at least, where are these important? Why are these important? So here, of course, is our citric acid cycle. We've seen this before. And you can see over here we have, alpha ketoglutarate, which is just a derivative of glutaric acid. There's carboxylic acid groups at both ends, and then 3 carbons in the middle. A couple carbons later, you can see we have not just a derivative of succinic acid, but succinate itself, which is just succinic acid that's lost its 2 protons. And in fact, throughout the entire Krebs cycle, pretty much every compound is a derivative of either succinic acid or glutaric acid. So a lot of these diacids, play some very, very important biological roles. How do we remember them? Well, this is the mnemonic I learned back when I took organic chemistry, and it's still the way that I remember them today. And so that'll give you, the first letter of each one of the diacids. All right, now the other group we're going to cover some nomenclature of in this chapter are nitriles. And how do we do nomenclature for nitrile? Well, what I would say here, and one of the things I try to do is, we've now done nomenclature of a lot of different functional groups, is I always try to compare it to, what other functional group have we learned that has similar rules? And, as we talked about earlier, the carboxylic acid's very, very similar to aldehydes. Well, nitrile nomenclature is probably most similar to thiols. And that's for a number of different reasons. If you recall when we named something like this, we called it butane to thiol. And the reason I choose thiols here as a comparison is because the ending on the parent name is literally just the name of the functional group. And that's why nitriles are a good comparison. Because the ending for a nitrile on the parent name is again the name of the functional group, nitrile. Now the other reason that I like to compare these two thiols is, if you recall, with thiols, if we had a higher priority group and the thiol became a substituent instead of part of the parent name, then in that case, not only did we move where the name went, but the actual term that we used changed. So for example, a carbonyl, such as a carboxylic acid, was higher priority, and so this compound would have become 2-mercaptobutanoic acid. Nitriles behave in the same way. If there's a higher priority group, then we use them as a substituent, but the term that we use to refer to them by also changes. So 2-mercaptobutanoic acid, now we've replaced the thiol with a nitrile, but because the nitrile is a substituent, we use the term cyano. And so what we have here is 2-cyanobutanoic acid.